Okay, section 3.3, complexity of algorithms. In the last section, we talked about a system to say this function is on this order. Well, now we're ready to put that uh, into action with actual algorithms. And we're going to talk about the time complexity of an algorithm. So this is measured in terms of the number of operations performed when the input has a particular size. Now, it might be the case that we'll talk about how long it will take on an actual machine in like a certain instance on a problem, but for the most part, that doesn't do us a lot of good, right? Because I want to be able to say that my algorithm works at a certain speed. And so if I have a faster machine, of course, it's going to be faster. So I kind of want to take that out of the equation. I just want to talk about how many operations need to be done. If the hardware gets faster, that's great. Note that we can also talk a little bit here about space complexity. That's how much room this algorithm takes, how much memory it would need to allocate to be able to do this. We're going to set that off to the side and just focus on time complexity. So for the most part, we're going to assume memory, if we need it, it's there. So what kind of operations are we looking at? Well, our CPU might be doing things like addition, multiplication, division. We might have to do comparisons or assignments, like readouts, reads into memory. We're going to be doing some real broad stroke stuff here, right? So while not all operations are the same, we're going to put them in the same bucket, right? Clearly, going to fetch something or going to assign something to memory can take a lot longer than a simple addition inside our CPU. But we, especially, if our RAM fills up and we got to read out to the hard drive, that could take a real long time. But again, we're not going to worry about that. We're going to assume if I want to compare two things, I've got them right on deck. We're going to assume that a division will take as long as an addition, because again, we're going for broad strokes here of how many quote unquote operations we need to do. We're going to put all these under the category of an operation. So we're going to assume addition, multiplication, division, comparison, they all require about the same amount of work, and we're not going to count reads to memory at all. So assignments are not going to be counted in the time complexity algorithms that we're going to do here. So let's look back at some of the algorithms we have and talk about their time complexities. So here's our algorithm for finding the maximum element. We were going to walk down the list and find the maximum. So reading the code, the first thing we're into there is the assignment of maximum to A1. Well, assignments don't cost us anything. Next, we get to the loop increment there. For I from 2 to n. This is a comparison, right? Is I greater than n and I plus plus. So we get an addition. So right there in the loop increment, we get an addition and a comparison. If the max is less than a sub I, comparison, then assign the max to a sub I. Assignment doesn't count, so we get one more comparison there. So the thing to handle next is, well, how many times is this loop going to run? This one's pretty easy. It's a for loop. It's going to run n minus 1 times, right? Because it starts at 2. So it's going to run n minus 1 times. Each time it runs, I get 3 operations. So the time complexity algorithm here is 1 addition, add 1 for the comparison, add 1 for the comparison, multiply that by n minus 1 because it runs that many times. I get 3n minus 3. So our maximum algorithm, that's a polynomial, is on the order of n. What about our linear search algorithm? Well, again, I get a loop increment there at the beginning. I get 1 comparison. How many times is this loop going to run? The issue here is the return I statement there, right? As we're looking down the list, we're supposed to say, aha, we found it, and then quit running the code. But obviously for us and analyzing the time complexity algorithm, that inputs a variable, right? We don't want to say, well, this works really fast if the thing you're looking for is at the beginning of the list and it takes a really long time if it's at the end of the list. That's not effective. So what we do is we talk about the worst case complexity often. So this is the maximum number of operations needed to solve a problem of a given size. So what's the worst case that could happen here? The thing we're looking at is not on the list. In that case, we would have to run this loop n times. So that gives me a algorithm, a complexity algorithm 3n, which is on the order n. Know that this means that our linear search and our maximum algorithms are of the same order. What about binary search? This was quite more complicated in theory, right? The algorithm was more complicated to implement. How's that going to pan out for our code, for our time complexity? Well, start reading through. I assigned to 1 doesn't count. J assigned to n doesn't count. While I is less than j, comparison. M defined to be the floor of I plus j over 2. Now, while not mentioned, I can clearly see there's a sum. So that's an operation. There's a division. That's an operation. And while not mentioned previously in our list, clearly the floor is going to have to be some sort of operation. So we'll just include that on the list. Right? You could do it as a compare if you wanted to. So floor function going to count as an operation. The if statement there. If x is greater than a sub m, so that's a comparison. And then I have this then else situation going on. Worst case complexity. If I fall into the else category, it's just an assignment, no additional operations. If I fall into the then category though, I'm going to do m plus 1. That's an addition. That's worse. So we would consider this to be one comparison, one addition. Back to the issue though of how many times does this loop run? This is going to be more complicated. Let's set that aside for just a second and look at the very end of the code there. If x is equal to a sub I, return these two different things, but that first one there is a comparison. So back to the big issue at hand, how many times does this loop increment run? Well, we're going to have to pull a trick here. We're going to assume that it is some multiple of 2. So if we had to, we could pad the data with zeros or something if we had to prove that this were the case. But remember, broad strokes here. So if we have 2 to the k elements to binary search, the first iteration has 2 to the k integers left to look at. Items left in the list, 2 to the k, right? We haven't done anything yet. But remember how the algorithm works. Each time we cut it in half. So when we go for the second pass, there's 2 to the k minus 1. When we go for the third pass, there's 2 to the k minus 2. We're going to keep cutting in half over and over and over again. Sorry, typo there. Should be, grab the pen here. One integer, right? We keep doing it until there was just one element left. So how many times does this run? It runs k times. I know what you're thinking though. K is that we can't just throw that into our equation, right? It's supposed to be, our algorithm is supposed to be based on the size of the input. K seems connected to the input, but how? How do we connect those two? It's going to run for k iterations. And you're forgetting a really basic definition that's easy to forget here. This is log. right? What power do you need to raise 2 to get to n? K times. Remember, in this course, that's log base 2. We're reading this as log base 2 of n is equal to k. So that loop runs log n times. So our complexity algorithm is 6k plus 1. Replace the k with log n. We get that it is a 6 log n plus 1 complexity algorithm. This is where we get the amazing fact then that binary search is on the order of log n. And if you think about it, it makes some sense. This is the amazing one where when you double the work, you just cause one more loop increment to run. And think about it. At each step, I slice this thing in half. So if I double the elements to look through, but they're in order, slice it in half, I get rid of them all in one step. All the doubled that you just add, I got rid of it in one iteration. Bubble sort. Now, here's where we're going to take another sort of deviation in how we're calculating these. Because we have nested loops, it's just going to make the arithmetic at the end harder to perform, but it's not going to change the order of the time complexity algorithm. So whenever we have nested loops, we're going to forgo including the loop increment in our calculations. So I'm not going to do the compare and the addition for the for loops. What I can say is that that outer loop runs from 1 to n minus 1, and the inner loop runs n minus I. So what I'm looking at for a complexity algorithm is the sum from 1 to n minus 1, where I'm adding up elements n minus I. Rewrite this. This is the sum from I equal 1 to n minus 1 of n, minus the sum from 1 to n minus 1 of I. Using our formulas from chapter 2, from sequences, we get this. N minus 1 times n minus n minus 1 times n over 2, which just leaves me with, right, I have a whole minus a half, I'm left with a half. So we're left with n times n minus 1 over 2. So bubble sort is on the order n squared. What about matrix multiplication? Now, even if you're not familiar with matrix multiplication, we should be able to trace the code for a problem, even if we're not entirely sure what it's doing or how it's operating. If you are familiar with matrix multiplication, this is the most straightforward way to multiply two matrices. But let's trace this code. Let's see what the time complexity algorithm is. Just like before, we're going to set aside the loop increments in this calculation because we have a bunch of nested for loops. We can see there, innermost loop, we do a multiplication and we do an addition. And that is going to run k times. Right, note that A is an m by k matrix and B is a k by n matrix. We need those, we need it to be of that form. We need those k's to line up. Next, we get an assignment to 0. That doesn't count, doesn't count towards our count of operations, but this is nested in a loop that's going to run n times. And finally, the outermost loop runs m times. So we have an algorithm here for our time complexity that's based on 3 variables, k, n, and m. Let's make this a little more simple for our case of conversation here. Let's determine the time complexity between two n by n matrices. In that case, our complexity algorithm 2k(n)m is 2n(n)n, so 2n cubed. So this means that the multiplication of two matrices is on the order of, or I'm sorry, is big O n cubed. This algorithm would be for an n by n matrix on the order of n cubed. As we're getting ready to discuss, this is the most straightforward application, right? If you're taking a linear algebra class, this is the algorithm they will teach you for multiplying these. This is not the most time efficient algorithm that has been created. In fact, you can get this down. The current fastest for matrix multiplication is on the order of x to the 2.37. To do that, though, there's always a trade-off with these things. The coefficient for this one's pretty big, so you would want these matrices to be very, very large before you'd be willing to pay the cost here. But note that this is a savings, right? It doesn't drastically change it away from polynomial speed, but if you're multiplying really big matrices, this helps a lot. Your computer does spend a lot of time in the background multiplying matrices. So what we tend to say is that if something is on the order of a constant, in this case 1, remember we can multiply that by anything in the big O notation scheme, we call it constant complexity. If it's on the order of log n, it's logarithmic complexity. If it's on the order of n, it's linear. If it's n log n, it's linear arithmetic. If it's n to the b, it's polynomial complexity. And you'll note that we broke that up into several categories, right? We were looking at quadratics and cubics and power to the 4, right? But all of those are roughly polynomial complexity problems. Then we got to ones that were b to the n, and that's where we started to see the crazy growth on our table before, where I said, hey, if you doubled the input, you got a constant raised to the n factor of increased output, and then factorial was even larger than that, right? I didn't even have a way to describe that. And that division line kind of has a name. A problem is tractable if it can be solved by a polynomial time algorithm. We tend to call any of these, right? If you're polynomial or better, you're tractable. It's sort of like saying acceptable. The algorithms above that red line, the exponential and the factorial, they're a problem. These are the sorts of problems that can be shown where you're like, hey, if you're going to do it this way, your computer would be running until the end of the life of the sun to try and solve. So we call anything that a class P if it is a tractable problem. So it's a problem that we have witnessed. We've come up with an algorithm that can solve it in polynomial or better time. Class NP is the set of all tractable problems whose solutions can be checked in polynomial time. So not that you can generate a solution, but you can check a solution. And let me give you a quick example of this. A Hamilton circuit wants you to start at one of these dots, and I want you to end at that same dot, but you can only go through the dots just once. And look at this graph and tell me if you can find a Hamilton circuit. Now, I didn't wait that long, and that's kind of the point, because I want you to compare how long you're looking, you're probably still looking as I talk, to me saying, is this a solution? And once you get a solution in front of you, it takes you no time at all to shake your head and go, okay, yep, that works. And that's the idea here. If you can look at it and say, that's a solution real quick, does that have any connection to being able to find that solution real quick? So NP-complete problems are a set of problems such that if any one of them can be solved in polynomial time, then all of NP can be solved by a polynomial time algorithm. So this connection, a lot of really intelligent people have been trying to do this for a very long time. And every time that they think they have a solution, it turns out that they've just found another type of problem to throw onto this NP complete problems, right? Every time I've got an algorithm, I think it's going to solve it. Nope, it goes on the pile of NP complete problems, right? So we're waiting for the dominoes to fall here. And it appears that there is no connection here, right? The literal $1 million question is P versus NP. That is, if you can check it fast, if you can check the solution in a tractable amount of time, can you find a solution in a tractable amount of time? So far, the answer is no. But there have been a lot of problems in the history of mathematics that it didn't seem like it was possible, and then somebody figured it out. That being said, you will note, just looking at how we've done our proofs in the past, it's harder to do an existence proof, right? It's hard to say this thing exists without finding it. And it's even harder to prove that something doesn't exist. So that part has not fallen either. We've not been able to prove that this is true. We've not been able to prove that this is not true. You can see here with the list of NP complete problems, we're waiting for the dominoes to fall. So I like to always end this section with some sort of hopeful message here. Maybe it's one of you that's going to go on to prove this, right? If you can show that P equals NP, it'll have some pretty major ramifications, and you get $1 million. So that's always nice too.